Sorry. Well, as the title let you guess, I will talk about ABC using the Wasserstein distance as a way to determine the difference between the observed sample and simulated sample. So I assume you have already attended the previous talks on ABC and won't cover too much the background. Okay, so the setting is I have a sample of size n, and I want to infer about the parameters that presumably generated this sample, which is true or not. Most likely it's not true, but we want to estimate either the parameter or the pseudo-parameter. So we have a model that is indexed by the parameter theta, and the only assumption is that this model or this family of distributions is such that we can generate new samples given a value of the parameter theta. So this is feasible, not necessarily cheap. Last week I was doing a talk where each new sample took 10 minutes to produce on the mainframe. But this is feasible, and so we can at least use some generations from this model to assess whether the parameter is likely or not for the actual data. There's a y1 to n. That would be the notation for the observed data. And we also assume that we're in a Bayesian setting, so we have a Bayesian background, so say a prior pi that is available both as a density, meaning if I give you theta, you can compute pi of theta, and to generate from this distribution. So let's say we have a proper prior. Okay, so that's the setting, and the only difficulty is that this model is such that we cannot write down the likelihoods of the sample given one value of the parameter. So ABC can be seen as many different ways, but let's say that this is an auxiliary variable method where we generate both a parameter theta and a pseudo sample z1 to n, and in the auxiliary sample is there to run the simulation, because in the end what we're interested in is this pseudo posterior of theta given the data, that is the marginal of the join of theta and z. And the reason for that being there is that because we don't have the likelihood, we replace the likelihood with this indicator function or something slightly more sophisticated, but essentially it is the same spirit. We have a rather crude non-parametric estimator of the likelihood, and this ABC marginal, which is an approximation to the posterior, is actually a true posterior when you replace the data with a ball of radius epsilon around the data. So we cannot have the true posterior, but we have another type of posterior that is, again, conditional on the data that is approximated this way. And the method operates on principle in the sense that if we could push epsilon to 0, and in some cases we can do it, then you recover exactly the true posterior. Okay. Now, in practice, it's not only impossible to push epsilon to 0, but if the data is complex enough, and this is correlated with the fact that the likelihood is not available, it's even very hard to get a small value of epsilon. And when you try to implement the method, it's sort of obvious that the smaller epsilon is, the rarer this event, and therefore the rarer the case where the pair has a positive weight. And so the more rejections you get when running the algorithm, and therefore the more costly it gets. So in complex models, just looking at the difference between the data and the simulated data, whatever the meaning of that norm, leads to computational difficulties or inferential difficulties. That is, epsilon is too large, we are too far from the posterior, so we don't exploit correctly the information contained in the data, and so we are running a poor inference. And so one kind of standard or golden standard in ABC is to replace the data with summary statistics, which primary reason to exist is that they reduce the dimension greatly, and therefore they push the proximity between the data and the simulated data to higher precision. That is, the epsilon here and the one there are not of the same scale because those objects are not in the same dimensions. And there is a rather neat literature on the selection of the summary statistics and the connection between the dimension of summary statistic and the speed of convergence of the ABC approximation. Namely, one is ABC inference coherent and consistent. Because in most cases, eta, this summary statistic, while containing information about the parameter, is not a sufficient statistic, and therefore, even if we were able to push epsilon to 0, we would not recover the exact posterior. So we have a different type of inference that is conditional on eta, and Gail pointed that out this morning. And we can precise in which cases this inference is coherent or consistent. Particularly, we can connect the value of epsilon with the number of observations and how quickly epsilon has to go to 0 for the convergence to happen. However, when you look at practical problems, there is not a very strong guideline or structure to select the summary statistics. And depending on the choice of the summary statistic, we do get a different output that may really impact the final inference. And sometimes you may get too restrictive in the dimension of eta and therefore lose identifiability. And again, if you are in a complex structure, it may be hard to establish that the parameter gets unidentifiable. In other cases, to avoid that danger, you may reach for a too large dimension of the summary statistic. So there is a definite curse of dimensionality that impacts the ABC methods. And again, if we start handling a large number of parameters or models with a lot of latent variables, complete inference may get complicated, and using ABC may result in poor inference, connected with the dimension and the choice of the summary statistic. And so one maybe paradoxical entry is to suggest that we could get rid of the summary statistics and look directly at the difference between the simulated sample and the observed sample. But rather than looking at a rather dumb distance directly between the vector of observations and the vector of simulations, especially in cases where the data is IID and the simulations are IID, the sample as a whole could be considered for computing this distance. And so by using the entire sample, but as a sample rather than as a vector of observations, we could produce smaller values of epsilon that are still representative of the problem of inference, and therefore push epsilons closer to 0 to get hopefully better inference. Even though there is another paradox in ABC, which is that epsilon should not be too small as well to achieve the right degree of approximation. So one naive illustration is the use of order statistics, namely that if you are in an ID problem, the order statistic is a sufficient statistic, and therefore rather than looking at the distance between the vector y and the vector z, one could look at the distance between the order statistics of both samples. That doesn't make much of a difference in terms of dimension, but still this brings the idea that what matters is this empirical CDF connected with the observed sample and the simulated sample. And of course, all kinds of versions could be proposed as well. So of course, I mean, numerically this makes a difference, but you can see that by ordering the observation, the variability of that distance will be much smaller than the variability of the other one. Okay. And so here is an illustration on a very toyish example, which is that if I take 1,000 observations from a gamma with chosen parameters 10 and 5, and if I assume that the data is from normal model, so on purpose I use a misspecified model, using a certain prior on both parameters of my model, the difference between regular ABC using row Euclidean distance and this ordered statistic distance is not so visible on the posterior for mu. Both of those posteriors are ABC posteriors. But if you start looking at sigma, there's a huge difference between the two. And the bar being the true value of the parameter, it's only the sorted L2 that recovers something close to the right value of sigma. And of course, that's an example with a lot of observations. But you can see that even in that situation, having a lot of observations does not save the day for this crude distance between the samples, because in that case, the noise takes over the information contained in the data, even though we have 1,000 observations. Okay. And so the notion that leads to Wasserstein distance is that this is one special case in the unidimensional case of Wasserstein distance between two samples, or between two empirical CDFs, the one based on the observed sample and the one for the simulated sample. And so that leads to the direction exploited in this paper, that transforming the sample into empirical CDFs in dimension 1 or D leads to a different type of distance that exploits the entire sample by removing as well some of its uninteresting variability. And in that sense, without containing completely the curse of dimensionality, we do reduce its impact on ABC in inference. So a few words about Wasserstein distance. I mean, as a general concept, it's a way to compare two distributions by looking at the maximal proximity between random variables from both mu and nu, rho being a type of distance, arbitrary type of distance between the points x and y. And then an extra calibration is a choice of the power p here and there. Okay. So fixing the marginals as mu and nu, one tries to figure out the best combination of those two distributions. So that's connected to Copula issues as well, to bring the two distributions as the joint distribution of the two random variables as concentrated on the marginal as possible, as we saw this morning as well. So one illustration in again, very, very toyish situation is, say, you take three atoms for two distributions. So you have y1, y2, y3, and z1, z2, z3 that are at those locations on the real line. And the question is how to weight jointly the pairs 1, 3, 1, 2, etc. to minimize this distance, this expected distance between the points. So you have to define a joint distribution, which here is a matrix with 6 entries, constrained by the fact that the marginals are 1/3, 1/3, 1/3. And so the minimization is the sum of those quantities, the rho y, z, j being the difference between the locations. Okay. And so in that case, by putting around all combinations, the best combination happens to be that y1 and 3 are together, 2 and 1 are together, and 3 and 2 are together for this particular numerical value. And so that leads to the optimal solution being in the matrix well, with only 1 entry per line, and this respects the marginal, the double marginal constraints. Okay, so that's one resolution. Actually, it's a special case of a general result that if you look at a distance between two empirical distributions or a distance between two samples, it is known that the optimal solution is that the weight goes to a single pair on each line. And there is an I missing in the formula, with weight 1/n. Okay. So that's a general result. But of course, we could generalize this to other situations. And in that case, we do get the Wasserstein distance as what I presented earlier, a distance between one order statistic and the other, except that here we take all possible permutations rather than just the natural one. Okay. And well, the difficulty is to extend this result in larger dimension than a single dimension. But of course, one solution is to always project back to one dimension by choosing the proper summary statistic. But because we want to avoid that arbitrary selection of summary statistics, this is not an interesting direction. But this becomes a bit of a harder problem, especially because there is no natural ordering in dimensions larger than 1 if we don't have further structure to exploit in the problem. So this relates to whole breadth of works in applied mathematics along the Wasserstein distance. But again, there is a statistical intuition behind that. It's not only a fad exploiting this trend in applied mathematics, namely that that's a way to define distance between samples or distance between a sample and a distribution that is as valid as other M estimation methods, namely that under some conditions we do get convergences of that kind. That is, if you look at the parameter that brings a distribution the closest to your sample, this estimator will converge at the regular speed, root of n, to the true parameter or the pseudo-true parameter if the model is misspecified. And there are asymptotic results as well. That's not such a recent result. Bassett et al. Have a paper in 2006. Okay. And just as a kind of stale joke, because it was last year, you can also use Wasserstein to go transport yourself to the French Parliament. Now, a common criticism of this approach is that Wasserstein is quite costly. And to some extent, it is correct that as the dimension goes above 1, the most common algorithm is of order n to the 3, which is a lot to contemplate, with some solutions in some situation being of order n to 0.5 log n, but that's under some conditions. But there does exist loopholes to exploit to bring either lower bounds or converging approximations to the exact Wasserstein distance. And so, for instance, there is a version that regularizes the original Wasserstein distance by an entropy factor of delta H of gamma, gamma being again the joint distribution, that reduces to N2, which is not yet absolutely fantastic, but that's a reduction. And then there are further and rougher approximation that will give something like n log n to compute the Wasserstein distance, and that's not something we can really improve. And Marco Couturier has proposals in that direction. Now, one mention that brings me back to the order statistic and the comparison of empirical distances is the use of projections from a dimension D back to dimension 1 being called swapping. But the one I just want to mention briefly is the Hilbert curve version. Namely that by designing a Hilbert curve on the sample space that you can reparameterize as an hypercube, you can transform, here is dimension 2, but a space of any dimension into a line of dimension 1. And again, that line, which is a measure of projection, computes an order on both samples. And so through the Hilbert curve approximation, we can compute a type of Wasserstein distance that will be an upper bound on the exact Wasserstein distance, but will be computable in n log n time. So this Hilbert curve is simply there to bring, say, 0.1 to the d back to 0.1 and define by the proximity to the curve of the projection to the curve an order statistic on multidimensional vector. So this sigma y and sigma z are the ordered observations once projected on the Hilbert curve. So that sounds a bit like unrelated with practical problems because you have to create this Hilbert curve, but actually in the quasi-Monte Carlo paper, red paper by Mathieu and Nicolas 3 years ago, they demonstrated that you can run SMC through the use of Hilbert curves. And actually, in our paper, we do use Hilbert curve to compute practically this distance. So this is feasible because actually, this is a concept that runs till infinity for a given sample size. It's enough to run the decomposition until all points are ordered. So there is a finite length and order to the Hilbert curve. Okay. Again, because it's a distance between empirical distributions. It has a computable version. The cost remains n log n. Surprisingly, the only construction that depends on the distance is the length, the construction of the curve itself. And it is 0 if the two samples are identical, but for a certain permutation. So that's an approximation that works. It has limitations, of course, because you project from dimension D to dimension 1. So if the dimension grows beyond some extent, it's not very accurate compared with the exact Wasserstein distance. But it brings a gain that can later be exploited when running ABC to provide a first approximation to the exact Wasserstein distance. And so if we assume that we are in situations where the exact or a more accurate version can be computed, it's a sort of delayed acceptance that can be produced through the much faster Hilbert curve. That is, we can reject already a theta if the distance is too large through the Hilbert curve approximation. Okay, so this version of ABC that we run is regular ABC, rejection ABC, where we generate parameters from the prior, then a pseudo sample from the assumed distribution, then a form of Wasserstein distance, possibly with this approximation. And then once we have run enough simulation, we do compute an epsilon that is a quantile of all of simulated distances. So the epsilon is estimated from the simulation. And one modification from the standard ABC that brings a clear improvement to the method is error-hit MCMC that was suggested by Anthony and then Anthony and Chris in these papers. That is just equally valid, but with better performances. Okay, so here is again an illustration on a simplish example of bivariate normal, where estimating the mean theta 1 using a summary that is sufficient, or using the true posterior, or using the Wasserstein, bring a very similar posterior distribution. Even though, of course, the Wasserstein is not using a sufficient statistic, but a modification of the anterior data. On the opposite, using the Euclidean distance, even though eventually it should converge to the posterior, for a given simulation time is much worse. Okay. And well, compared with using the summary, the Wasserstein is not losing very much as the number of simulation grows. There is another example that you find in a lot of ABC papers. I still consider it as toyish. It's slightly more challenging, but as Pierre showed a few years ago, you can conduct a lot of computations exactly without any approximation. So there are 5 parameters in the model: A, B, G, Z, and K. And again, I won't go through all the pictures, but for most of the parameters, there is a strong similarity between the posterior and the Wasserstein approximation for a given simulation time. And the distance to the model is roughly similar for the different approximation that we use, even though the computing time is much better for either Swap or Hilbert. Okay, a few words about asymptotics, which is what happens if you lead the number of parameters to infinity. As I mentioned, there are already results in the literature that if there exists a parameter or pseudo-parameter that brings the model as close as possible to the generating distribution, this Wasserstein estimate, that is a minimum of this distance, will converge almost surely to this pseudo-true value. And you can improve this convergence with a form of central limit theorem as well that you can recycle for confidence interval. And so here is a comparison, although it doesn't mean much because that's just a simulation of using the MLE and this minimum Wasserstein estimator. And in this example, you can see that the variability is approximately the same for MLE and minimum Wasserstein. Now, in most cases, it's not possible to compute directly the minimum Wasserstein distance estimator because the distance between the sample and the distribution is not available. And it's much easier to compute the distance between two samples, as I already discussed. And if this is feasible in a reasonable time, you can consider instead the expectation of this distance that can be approximated by Monte Carlo. And so that's the minimum expected Wasserstein estimator, that is a more practical version of the MWE. And in that case, we can reproduce most of the convergence result under stronger or even stronger assumptions. But there is convergence of the estimator theta hat to the pseudo-true value of the parameter as n and m being the number of Monte Carlo simulations for the expectation as n and m grow to infinity. And again, that's an illustration for the G and K distribution. Okay, I think I'll just skip that. I'll come back to it later, but I just want to mention a few words about a slightly more complicated case, which is the case of time series. That is, if the data is not IID, so if y1 to t is a time series, so with dependence between the y's, how do you compute a Wasserstein distance? And so in the paper, we study 4 different approaches. The first one is not really a solution. It's just forget about dependencies and process the sample as if it was an IID sample. The difficulty with the solution is that you may have this sort of situation where part of the parameter vector is not identifiable. And so you get a very nice concentration on a curve, which is sigma square over 1 minus phi square equal the true value in that case. But you cannot identify sigma and phi. So that brings some information, but not the complete information about the parameter. Another approach is, common to some Markov and hidden Markov model. That is, instead of looking at the data as such, you create a vector of lags, say yt minus 1, yt minus k, and each and the data is now the collection of those vectors. So there is a lot of overlap between the observations, but by increasing the dimension, you do recover identifiability if you push the lag far enough. So that depends how much you know about the model, but for the same example as previously, the AR1 example, then you get the concentration for a lag of 2. Okay, you just need to look at yt minus 1. That's your new observation. Combining Wasserstein with this new observation brings you this outcome. Another version that is only applicable for some generative models is to reconstruct the white noise behind the data. That is, if I give you theta and y, in some cases, in a generative model, you can reverse engineer the derivation of y back to the w's. And those w's are IID by construction. And so you can look at the Wasserstein on the reconstructed w's. And of course, for simulation, that's much easier because they are already and directly available. They are, for instance, a sequence of normal 0 1s. Okay. And so there are fewer examples where this works, but for some intractable problems, this was a solution we attempted a few years ago in an empirical likelihood ABC with Kerry Mengersen and Pierre Prudlot. And so in this example, for instance, we do manage to reconstruct the white noise behind the data and look at the distance between the two white noises, or directly the fact that this reconstructed white noise has the right distribution. So we just need one sample. And as the number of simulation grows, we do get a concentration around the true value of the parameter. But of course, that doesn't work for all situations. And the last method I want to discuss is somehow orthogonal to to the others, and it may seem going back away from the notion of sample, namely curve matching. Rather than considering the sequence of observation as something inspired from an IID sampling and derived by a transform, curve matching considers the whole sequence as the observation of a curve indexed by both t and y of t. And so the distance is now between the pairs as a vector, tyt and tzt. For instance, using this penalized type of distance, when lambda is equal to 0, it's back to the bad original sequence. And if you push lambda higher, then you impose a constraint on the time as well. And so if we use this different distance, we do get another Wasserstein implementation. And if we get back to the cosine example as previously, we recover better than the Euclidean by this penalty factor of curve matching. Because actually what matters is the shape of the curve rather than the precise location of the points. And Euclidean, or at least in this particular direction, does pretty poorly. Okay, so I'll stop here to say that this is not a solution that works in every situation and for every problem, because it is still dependent on the dimension of the parameter. That is, for large dimensions, it is not a feasible or practical solution. But still, we have one for one large class of problems, including time series, and possibly extension like spatial data or images. We do have a way to construct comparisons of samples and pseudo-samples that remove part of the noise contained in the data with some theoretical guarantees, with some speed of convergence of the tolerance to 0 to achieve consistency, and still manageable in a finite time, as shown in the computer codes that are associated with a paper. So that's an open direction that I find interesting because it just shies away from any selection of summary statistics. That's not the only direction, and projections that are automatic through machine learning systems are also of interest, but for complex data, that may be still a quite interesting direction. Thank you.
Okay, we have time for questions. There are two questions. So in one of your plots, the GNK plot, it was seems to be okay except one, which was
Yeah. Is that one? No. The other GNK. Yeah.
There is one, so this G2 seems to what happened.
So G2, yeah, you're right. G2 is not good. I have no explanation except, G2 is well hidden in the distribution. So it's maybe that these were one and two are for two different data sets. No, I cannot tell one. It's just it's not an easy parameter to estimate because it's not. This is location scale, so this is free. You don't need ABC essentially. But G and Z are not as well. Z is a transform of R, but this is like third degree parameter, a bit like like a skewness parameter. Yeah.
Second question is that in GAN, they use slash passage distance, so they use one of projection of the set. So in order to cope with the
Dimension?
so they use the slash passage distance, with, so it becomes very popular this year. So talks of paper time, you try to, so basically you project
Yeah.
projection and you then compute passage distance in function 1, which is
Mm-hmm. And then you take the minimum?
yeah, no, they combine, so there are several versions, but they slash passage distance, and they're in GAN, and nobody now the passage GAN slash passage GAN.
Well, I think, I remember Pierre discussing it, but I think he had a good reason not to look at it. But I mean, yeah, this Hilbert projection, again, you can use it in there is an arbitrariness in the choice of the curve. So you can define, depending on what you call first axis, second axis, and so on, the ordering of the basis in the hypercube has an impact. So you could do that for a collection of Hilbert curves. I'm not sure it would bring much again, because it's like these projections, they are not inspired at all by the structure of the model or the data. It's purely, it's totally blind. But having several several approximation to Wasserstein is always an interesting thing, because you can start with fast solutions to improve epsilon, and because some of them are comparable with the exact Wasserstein. So, I mean, some are not, but when they are, they bring you up a bound, and so that's quite useful to start running the algorithm. Yeah. Yep.
So you mentioned that in your example you cannot compute your Wasserstein distance, and then for that you compute the expectation of the Wasserstein distance.
Yeah.
Is that right?
Yeah.
Okay, so I'm wondering if this is like the Fresemi, is that what it is?
The what?
The Fresemi.
Fresh, I mean.
Yes.
Oh, okay.
Is that what
I've no idea.
I'm sorry?
I've no idea.
Okay. So because if
The fresh, I mean.
if that's what it is, it's like I'm wondering about the uniqueness of this expectation. Is it unique because it's overset now, right?
Well, it's unique. If I write E of D mu hat, say nu hat 1n, I mean, this is a random object, and so that's defined uniquely. So I don't really understand in which sense it would not be unique. Sorry, I may miss something.
This is like a 1-1 correspondence with a Fresemi, basically. But that's not the idea.
Well, I have no idea what is a fresh mean. So.
All right, maybe we can go back to that.
Yeah.
But the second question is, when you mentioned about the Takens, when you turn the time series into a point cloud by using this Takens algorithm,
Yeah.
Takens theory, dynamical systems, the lag that you select is of paramount importance.
Oh, yeah.
I'm kind of wondering, how do you estimate that?
We don't estimate the lag. In the example we ran, we just increase the lag until we see.
Embedding, right? That's what we did. It's the embedding theory. The Takens algorithm is the embedding algorithm, basically, where you select this kappa, this lag. So do you do it arbitrarily? You select some lag?
No, we do it. We increase the lag until we see the concentration. So you start with 2, and then you can just increase. So it's very down to earth. So you mentioned that there could be a more elaborate way to to estimate this lag?
Could be maybe through the autocorrelation function. So like you can plot the autocorrelation function of the time series.
Yeah.
And whether it's maybe you see like a significant dip in the autocorrelation function, significant change, maybe you can select that as the lag. So when you do the embedding, you do, let's say, that was the point 10. So you do the embedding YT plus 10.
Mm-hmm.
But that's kind of empirical. So I'm kind
Yeah,
of
it's similar. No, we are doing something empirical, but in a different empirical. Looking directly at the posterior, at this pseudo-posterior, as a measure of this lag. Yeah. Now, of course, there's a limit to what you can do because this increases dimension very quickly, obviously.